Hi everyone, welcome back. Today we're going to continue our discussion on plane waves. So this is lecture 18. Plane waves 2, see? Okay, so last time we looked at plane waves in a homogeneous medium, we looked at k-space, we looked at the diffraction limit, so on and so forth. And a little bit, we spent a little bit of time on discussing evanescent waves when kz becomes imaginary. So today we want to kind of generalize that notion, see where else evanescent waves can come from, what do they look like, what is their behavior, and so on and so forth. Okay, so to do that, we will discuss plane waves in a lossy medium. Okay, so we saw that evanescent waves can exist even in a lossless medium, but in general, they appear more often in a lossy medium. Okay, and maybe it's easier to study it from that perspective. So we know that loss corresponds to a complex epsilon, right? So essentially, epsilon has a real part and an imaginary part. And since k is equal to omega square root of mu epsilon, k also becomes imaginary, complex. Okay, so essentially, we will treat the lossy material as a material that has complex k. Okay. Okay, so when k is complex, I can write it as two parts. I can write as beta plus I alpha, right? Real part and an imaginary part. This is usually done for waves that have it doesn't need a box. So this is for waves in 1D problems. So basically waves that are propagating, let's say, in a transmission line and so on. This is not very convenient for us because we have waves that are propagating in 3D, for example, a plane wave in a given direction. So what we really want is we want a complex k vector, right? We want a complex wave vector rather than a complex wave number. So we'll write this as k prime, which is a real wave vector, plus I times k double prime, which is a complex or the imaginary part of your complex wave vector. Okay, so keep in mind that k is equal to magnitude of k vector, but beta is not equal to magnitude of this. And similarly, alpha is not equal to the magnitude of k double prime. Okay, so what is beta and alpha? Beta is the real part of the magnitude of k prime plus ik double prime, which turns out to be the real part of square root of kx prime plus I kx double prime square plus ky prime plus I ky double prime square plus kz prime plus I kz double prime square. Okay, it's the real part of this whole thing, right? Because this magnitude here is the magnitude with respect to the vector magnitude. It's not the complex magnitude. Okay, so that's the length of that vector. Okay, I just want to mention that it's not really relevant because we won't deal with beta and alpha, but I just wanted to be aware that it's not the same thing. Okay, so I'm going to erase this. And we'll continue our discussion by basically treating k as complex k vector. Okay, there we go. All right. So we saw that phi, the phase for a plane wave, is this term k dot r, right? And we saw that the gradient of the phase is nothing but k. Right? So k essentially represented, when it was real at least, represented the direction of propagation of the phase, in which direction the phase is propagating. But now that k is complex, what does this mean, right? What does complex direction really mean? To answer this question, it's really not that difficult because essentially have two directions now. One which is the real part of k, which is the direction of k prime, and then k double prime also gives you another direction. So we need to interpret what these two different directions mean. Okay, so to interpret that, we go back to our definition, E, which is E naught e to the I k dot r. That's nothing but E naught vector e to the I k prime plus I k double prime dot r. This is equal to E naught e to the I k prime dot r times e to the minus k. Now we don't have an I there. E to the minus k double prime dot r. Right? So if I rewrite that, I have E vector equal to E naught e to the minus k double prime dot r times e to the I k prime dot r. E naught hat. Okay, so this is the polarization. This is the phase term. And this whole thing is the amplitude term. Right? Okay, which means what? Which means k prime is normal to equiphase surfaces right? Because you take the gradient of this, and that is along, or you can take the gradient of the whole thing, and that's along k prime. If you take the gradient of this, which is the amplitude term, that gives you k double prime, right? And k, maybe I'll use k double prime is normal to equi-amplitude surfaces. Right? So you essentially have two directions in the k vector. The real part of the k vector is the k prime vector, which tells you in which direction phase is changing the fastest, or the direction of propagation of the phase. And k double prime tells you the direction of propagation of the amplitude. And these two need not be the same when you have a lossy medium. In fact, they are not the same for a lossy medium. Okay, so with this, you can define something. When k prime and k double prime are in the same direction, those are called ordinary plane waves. Or I should say not ordinary, they're called uniform plane waves. And when k prime is not in the same direction as k double prime, those are called non-uniform plane waves. Okay. Okay, so let's take some examples, simple examples. So the first one, of course, is if k double prime is equal to the zero vector, and the zero vector is perpendicular, parallel with the k vector. Because it's a zero vector, you can put it in any direction, right? So maybe I'll just remove this. If it's a zero vector, then you end up with just the real k. And this is your classical plane wave, propagating plane wave, right? Simplest case. That's kind of trivial. Second example is when k double prime is perpendicular to k prime. Right, so we'll take an example of that. So we have k double prime, let's say, is a zz hat, and k prime is, let's say, along the xy plane. The xx hat is k yy hat. Then if I substitute it in, my e vector becomes e naught, e to the minus kzz, e to the I kxx plus kyy. Right? And this we saw earlier is the evanescent wave. So for an evanescent wave, propagation of phase is perpendicular to the propagation of amplitude. And that should make sense because if you look at the way evanescent waves propagate, right, there is a decay. So decay, let's say, in this direction, which is z direction, but the propagation was always in x direction. Right? If k was real, kz was real, then the propagation was, let's say, in this direction. And now if kz becomes imaginary, then you have a decay in the orthogonal direction. So surfaces of constant amplitude are these ones, but surfaces of constant phase are these ones. Okay? So the same exact solution is obtained when you have kx squared plus ky squared greater than k squared. Okay. So we said that evanescent waves in the last lecture, we showed that evanescent waves can exist even in a lossless medium. And that's true. We showed that earlier. But here we kind of derived it assuming there is some loss. But really what we assumed is that k is complex. Right? So that treats the general case. Okay, so when you have evanescent waves propagating at the interface between two media, they become surface waves. Sometimes they're called as surface waves. Okay, so essentially we'll see this later when we do dielectric air interfaces or dielectric interface or waveguides. Essentially you have some dielectric medium, maybe epsilon1, epsilon2, and we'll see that there's an evanescent wave that can propagate at their interface. It's exponential in this direction, exponential in this direction, but it can propagate in that direction. Okay. Now, if one of these dielectrics is a metal, and so if I have an interface between a metal and a dielectric, then these are called surface plasmons. Okay, so surface plasmons are basically nothing but evanescent waves or surface waves that propagate at the interface between a metal and a dielectric. The reason it's called plasmon is because metal kind of behaves like a plasma. So we haven't discussed plasmas yet, but essentially it's like medium which has free carriers. So metal obviously has free carriers because it has uh, free electrons, which it behaves like a plasma. Essentially for a plasma, epsilon is less than 0. And we know from the Drude model, which we saw several lectures ago, that for a metal, epsilon is less than 0. And when it becomes equal to 0, that's called the plasma frequency of the metal. And then above that, it behaves like a dielectric. So essentially, that's why they're called plasmons. Okay. Sometimes they're also called surface plasmon polaritons. It's really just the same thing. It's nothing but these surface waves. This term polariton comes in because there is also a wave of the charge carriers. Okay, so here we're talking about electromagnetic waves, which is this one. But because of the electromagnetic wave coupling to this metal, which has charge carriers, even the charge carrier inside propagates like a wave. Okay, they move like a wave. And then those are called polaritons. And that's why this whole thing is called a surface plasma on polariton. So it's a combination of the electromagnetic field and the charge carriers inside. Okay, but the phenomena is all the same. Okay, so it's also useful to look at the Poynting vector of evanescent waves. So this is always sort of confusing, first time when you learn about evanescent waves, the question becomes, do they carry power, right? So we can look at that. So I won't go into a lot of the details, but skip some of the steps which you can kind of do on your own. But let's say I have something like this. So I have a propagation in X of the phase and then exponential decay in Z. Okay, so that's just without loss of generality, you can align your coordinate system that such that the evanescent wave has phase propagation in X and amplitude propagation in Z. Then also let E naught be equal to Ex x hat plus Ez Z hat. So this is called a TM wave, which we'll see later in the next lecture. But today I'm just choosing this case. There's another case, which is the TE case, which you can also choose, but that's what I'm choosing for now. So I have some kind of, let's say, an interface, the XY plane, and then I have this exponential decay along Z, and this surface wave is propagating like that, right? So it's just X, let's say, no Y. Okay. Then you can calculate your H, or the H would be given by some HY hat, and this is again for this TM wave. And you want E and H to be perpendicular to each other. So that's why you get H like this. I'm writing H as HY hat. Now you may ask, okay, why is E not perpendicular to K, right? So the reason behind that is that in an evanescent wave, actually E and K are not perpendicular. They can have components in with respect to each other. Okay, so we're treating this case where you have an evanescent wave, and it's Tm, which means E and H are perpendicular, but they don't have to be perpendicular to K. Not necessarily. Okay, so these are my fields. Now I want to find what is this Ex, Ey, Ex, Hy, and Ez. And you can find that. So you can set divergence of E to 0. And from that, you can easily show that Ez is Ikx over Kz, Ex. And then you can also find H from I over omega mu curl of E. And from this, you can show that Hy is basically equal to Ik square over omega mu Kz Ex. I'm going to skip some of the steps, but just some simple algebra to show that. Calculus and algebra. Okay. So from these equations, you can write down E and H again. E turns out to be Ex, x hat, plus Ikx over Kz, Z hat. This should be bracket here. E to the I Kxx minus Kzz. And H vector is Ik square over omega mu Kz Ex y hat e to the I Kxx minus Kzz. Okay. So now we can calculate the S vector, which is nothing but E cross H conjugate. And if you do this, you will get, and write it as two terms, Sx x hat plus Sz z hat, right? Because obviously you don't have any y. because when you do x hat cross y, you get z, and z hat cross y, you get x. So you don't have any y component left. So if you calculate the terms, you get Sx equal to Kx, K square over omega mu, Kz square, mod Ex square, e to the minus 2, Azz, and Sz turns out to be minus Ik square over omega mu Kz, mod Ex square, e to the minus 2 Kzz. And from this, you can see that propagation in x is real, propagation in z is imaginary. Okay, so what does that mean? That means that if you calculate the time average Poynting vector, which is equal to 1/2 the real part of S, that would be 0 for Zs. So this will only have an Sx component. Right? So what does that mean? That means that if I have that interface, an exponential decay in that direction in Z, that means that in this direction, there is no wave propagation, power propagation, right? So power only flows along the surface. And if you go across the surface, there is no propagation of power. There is just power oscillating back and forth, right? So you can think of this direction, it looks like a capacitor or an inductor or an LC network or something like that, right? Where power is being stored, where energy is being stored, but there is no power flowing in that direction. Power is only flowing in this direction. Okay? So energy is stored in this evanescent wave, but power cannot flow through it. So there's no power flow in that direction. And that makes sense, because if I put a box here, very large box, then power that's entering, if it is flowing in this direction, then it must leave. But we know that the field goes to 0, so it cannot leave, right? So you can't have power coming in and then nothing happening inside, no power going out. Right? Whereas in this direction, it can flow, because whatever is coming in here, you have the same field out here, so it can go through, but it cannot go through like that. Okay. How do you actually excite these evanescent waves? Well, that's the next topic. That's not very easy. Why is it not easy? So we saw that, Kx, for example, is greater than K for an evanescent wave, right? So if I have an evanescent wave that's propagating, phase is propagating in this direction, then my Kx in that direction is greater than K. Let's say there's no Ky, right? So if Kx is greater than K, Ky is 0, how do I excite it? But later on, we'll see in order to excite a given wave, you have to satisfy a condition called phase matching. So we'll see that in the next lecture. So this phase matching property basically guarantees, or not guarantees, it's a required property in order for you to kind of transfer energy from one wave to another, which means to excite that wave. So which means that, what does phase matching mean? Phase matching means that if I have some incoming wave coming in that has some k vector, if I look at that k vector in this direction, right, which would be k sine theta, let's say, right, where this angle is theta, then this k sine theta must be equal to my kx. So the evanescent wave that I have, that one has a phase propagation in that direction. If kx for my evanescent wave is equal to k sine theta from my incoming wave, then I can have phase matching. So if this incoming wave is coming from free space, then this can never be possible, right? Because k is always greater than, kx is always greater than k sine theta, or greater than k. I should say that if this this wave, incoming wave that's exciting this evanescent wave is coming from free space, this is always less than k, cannot be equal to k because of sine theta, or less than or equal to k, I should say, right? Whereas this is always greater than k. So this equality can never hold, right? So one way to fix this problem is to have this incoming wave coming in a dielectric. So you make this side dielectric and you make this side free space, and then your incoming wave now has a k, or I should say, let me redraw that. We will deal with that case. So maybe I should first write out what are the different ways to do it. So the first way to do it is use a dielectric. Right, so for a dielectric, K is greater than K naught, which is free space, right? Because K is nothing but square root of epsilon r K naught, right? So this can be increased such that it goes beyond K naught. So in this case, maybe this is K naught, right? And then you can get that to work. Okay, the second case is using a grating coupler. So we won't deal with this in this class, but basically take an optics class. You'll see that there's a periodic structure that you can put in such that an incoming wave, which has some k, and by looking at the spacing of this, which is 2 pi by, let's say, capital lambda, this gives you a k capital lambda, which is the coupler k. Okay? And then there is a condition that this structure satisfies such that essentially you can boost the k of your incoming signal such that it can excite this plane wave, or this evanescent wave, or the surface wave. Okay, we won't deal with that here, but I just want to mention it. And the third one is using a slow wave structure. So what is a slow wave structure? It's a structure that can slow down the speed of light. And since k is omega over v, where v is the velocity, if I slow it down, then essentially k can be large, and then you can probably match to the evanescent wave, phase match to the evanescent wave. So there are three ways. We'll just deal with the first way today, in this course at least, which is using a dielectric. Okay, so what's the configuration? So let's assume I take a prism with some dielectric constant epsilon, and I have an incoming wave that comes in. It's this surface here, and then undergoes total internal reflection, which hopefully you've seen before. If you haven't, we'll include that in the next lecture. But essentially, when you come in at a steep angle inside a dielectric with high dielectric constant, the wave gets fully reflected back. Okay. Now, my claim is that this would excite an evanescent wave on the other side. An evanescent wave like that. Why is that? Because that evanescent wave is propagating, let's say, mostly in free space or in free space. So it's k x of this evanescent wave, right, is greater than k naught. And my incoming wave now is in a medium. Right? It's coming in at some angle. So this is theta. Then for my incoming wave, the x direction, the x component of k is k naught square root of epsilon r. This is epsilon r and sine theta. Right? And if sine theta is large, it's close to 1, let's say, and epsilon r is also large, then this thing can be greater than k naught. Right? Which means that you can potentially have kx evanescent equal to k naught square root of epsilon r sine theta. Okay, and then your phase matching condition is satisfied, so you can have this evanescent wave excited. Okay. If you're not convinced with that, you can also convince you using a thought experiment that there is indeed a evanescent wave propagating on the other side. So what is that, right? So let's say I take my prism again. Now I have this wave that comes in. All of it is reflected back, right? Now if I take another prism, I place it on the other side. Something like that, right? What happens? I mean, if I bring this, let me actually do that again. So maybe I just make a copy. I might just draw it again. So I have another prism like that. Move this down. Okay, this. So what I do is I take this prism and I slowly bring it closer and closer and closer. Okay, bring it closer and closer and closer, and then they eventually touch. So when they touch, what should happen? When they touch, you end up with essentially this shape, right? So if I have that shape and I have an incident light, that should just go through. But it should not reflect at all. Because let's assume this is 90 degrees, this is 90 degrees, it is 90 degrees, this is 90 degrees, and so on. So of course, if it's incident at 90 degrees, it just slows down inside the medium and comes out the other end. Right? So what I'm saying is that trying to make a copy of that again. It went away. Okay, what I'm saying is that basically when I brought this prism closer and closer, all of the power was being reflected back 100%. As it got closer and closer and closer, still 100% reflected. And when it touches, all of a sudden 100% is going through. And that doesn't make sense, right? I mean, what if it was just 1 nanometer away, 1 picometer away, or 1 femtometer away? Still 100% of power goes through, reflects, and then just as soon as it touches, all of it goes through. That seems kind of unphysical, right? It should be some kind of a continuous process where all of it is being reflected, and as you get closer and closer, some of it goes through, most of it is reflected, and then slowly, slowly, this is grabbing more power, very little is reflected, and eventually all of it goes through. So that should be the slow transition between these two cases. Right? And that transition is only possible if you have an evanescent wave. Because if I go back to this guy, when I have an evanescent wave that's decaying here, then some of that evanescent wave enters this other prism and starts to propagate in this direction. Okay? So essentially, what we get is this evanescent wave is grabbing some of that power and starts propagating in this other prism. Because once it enters the other prism, then it satisfies the phase matching condition and becomes propagating again, right? So as you bring it closer and closer now, exponentially, this grabs more and more power because this evanescent wave is exponential, and then eventually it grabs all of it once you touch. Because that's a nice kind of thought experiment that allows you to do that, to see that there is, in fact, there has to be an evanescent wave or some kind of a field on the other side. Okay, this actually brings us to a very nice application of evanescent waves, which is now $1 billion industry or multi-billion-dollar industry, which is called surface plasmon resonance. SPR. And you can look up that. You want more details, but I'll just explain the basic idea. So the idea is this: you have a similar kind of dielectric prism, and then there is a metal coating, thin gold coating on top of this prism. And the gold coating is there so that you can excite these surface plasmon resonances. That's why it's called surface plasmon resonance. And then on this gold coating, there are these ligand bonds. Okay? You can think of them as some kind of chemical bonds that are placed. And these chemical bonds can only bond with a certain molecule. Okay? So there is a certain molecule, let's say, that can bond to these bonds, right? So what you do is you want to detect the presence of this molecule in some liquid. Okay? So you have some liquid flowing here, which contains these molecules that you want to detect. Okay? So what you do, so you want to see, okay, this liquid, does it have these molecules or not? You take a laser light, laser source, single wavelength laser source, and you illuminate this entire structure like that. Okay? So of course, this gets reflected and then comes out something like that. Then you have a big detector on the other end. Let's use a different color. You have a big detector placed here, and that is detecting this reflected light. Okay. So essentially, there is one angle at which phase matching condition is satisfied. Maybe this angle, right? So at this angle, this condition of K surface plasmon along X is equal to, or not along X, let's just say K surface plasmon is equal to K naught square root of epsilon r sine theta. So only for one angle, that's true. So at that angle, this wave comes in. So this is the angle, theta, and then it becomes a surface wave. Right? For all other angles, that's not true. So all the other angles don't satisfy this condition, so they don't excite surface waves, which means they get reflected back. Only that one angle becomes a surface wave. So if you actually look at the power that is measured on this side, a lot of power is measured here, and there's a big dip in the measured power, and then again it goes down. And this dip corresponds to this angle. Okay, so essentially when these molecules bond, they change the dielectric constant that this surface sees slightly. When that dielectric constant changes, this surface plasmon resonance changes, KSP changes, which means theta changes, and you can measure that here. Okay, so this is a form of spectroscopy. And it's a very sensitive setup because that surface plasmon resonance is very sensitive. Okay, so this is called a Kretschmann configuration. There are other configurations as well of this surface plasmon resonance. And it's a very popular way of doing spectroscopy of these specific molecules. Okay, so that's about our discussion on complex K and evanescent waves and propagation in lossy media. Next, we will look at propagation in anisotropic media, and we'll see that there are quite a few interesting properties even there. Okay. Plane waves in anisotropic media. Okay, so just to remind you, anisotropic media is when epsilon and mu are tensors. B is mu tensor times H, right? So in this case, we'll just consider epsilon to be a tensor. So I'm going to simplify this as a scalar. Okay, so we go back to our wave equation. minus k square epsilon r tensor E equal to 0. And now divergence of E is not 0, right? Only divergence of D is 0, but divergence of E may not be 0. So you can't simplify this to just vector Laplacian. So we have to deal with this full thing. Okay. So we want solutions of the type solutions of the form E naught e to the I k dot r. So these are our plane wave solutions. So what do we have to satisfy in order to get that? So we saw that in free space or in homogeneous medium, homogeneous isotropic medium, we have to satisfy the dispersion relation. So we want to see what is the analog of the dispersion relation for an anisotropic medium. Okay, so we know that this curl operator is a matrix. So I can write it as dz, ddy, ddz, 0 minus ddx, minus ddy, ddx, 0. So I can, take square of this matrix because I have curl of, right? So that gives me a matrix. So this becomes a matrix. And now this is also a matrix. So I can pull my E out and I can apply this curl of operator on this thing, right? Pull my E naught out, sorry. I can pull the E naught out, can apply curl of matrix, which is a matrix onto this term. And then I also have this term as well. And that whole thing gives me a new matrix equation, right? So I'm going to skip the details and just write out the final matrix equation, which is a little bit long, but I can do it. That gives me ky square plus kz square minus k square epsilon xx minus of kx plus k square epsilon xy minus kx kz plus k square epsilon xz. Then you have minus kykz, sorry, kykx plus k square epsilon yx, kx square plus ky square minus k square epsilon yy minus kykz plus k square epsilon yz minus kxkz plus k square epsilon zx minus kykz plus k squared epsilon zy, kx squared plus ky squared minus k squared epsilon zz, whole thing times E naught equal to 0. So I shouldn't put a cross here, I should just put times E naught equal to 0. Okay, so that's the equation that's just the wave equation basically, under the condition that we're looking for these plane wave solutions. So we have a matrix times a vector equal to 0. Now we know that for this to be true for any E naught, to get a non-trivial solution, we need the determinant of this matrix to be 0, right? So delta, which is the determinant of this whole thing, must be equal to 0. Okay. So essentially, if you do that, this gives a dispersion relation. Right? Because this is just a relationship between kx, ky, kz, and k, along with epsilons in there. Similar to what we had for the simple case, which was the xk square plus ky square plus kz square equal to k square. Okay, so instead of treating this whole thing, we can treat a special case which is a uniaxial medium. Okay, so we know that in a uniaxial medium, we've seen that before. Epsilon r is epsilon x, epsilon z, and the rest are all zeros. Right, so typically, in many cases, you can find a coordinate system and diagonalize the epsilon matrix to be diagonal, epsilon x, y, z. But in a uniaxial medium, we say that, okay, epsilon x and epsilon y are also equal. We've seen that before. So in this case, the determinant becomes minus k square, epsilon xk square, minus kx square, minus ky square, minus kz square, times epsilon x, epsilon z, k square, minus kx square, minus ky square, minus epsilon z, kz square, and we can set that to 0 to get our dispersion relations, right? So for this to be true, this has to be 0 and this has to be 0, right? So we can write two equations, two different solutions basically. So I'll write it in a new page. So it implies that we have two solutions, kx squared plus ky squared plus kz squared equal to k squared epsilon x and kx squared plus ky squared plus epsilon z over epsilon x kz squared equal to k squared epsilon z. Okay, so this is known as the ordinary wave, and this is known as the extraordinary wave. So essentially, we're saying that in this kind of a uniaxial medium, you can have two different solutions that give you plane waves essentially, or some kind of a plane wave. One of them is called the ordinary wave, and the other one is called the extraordinary wave. Okay. So how do you actually understand this? So in terms of k-space, this one is a sphere, right? So ordinary wave is a spherical k-space, or I should say k-space is a sphere. Okay, so which means that no matter which direction this wave is propagating inside the medium, it has the same k, has the same magnitude, which means it has the same wavelength, which means it has the same speed. Right? Whereas the extraordinary wave, k-space is not a sphere. K-space is a spheroid or a toroid. Right? It is a circle in the xy plane, but it's sort of oblong along kz. Either it's oblong or it's squished. Right? It could be either like a flying saucer, like a UFO style, or it could be like the American football style. And depending on what epsilon z and epsilon x are. Right? So I would say maybe that, rather I should say this is like pancake rather than UFO. Okay? So which means what? Which means that depending on which direction I'm propagating in, I can have a totally different wavelength. The wavelength can change, the speed can change, right? Similarly to this one, depending on the direction of propagation, the speed can change or the wavelength can change, right? Which means the effective epsilon in that direction is different. The effective refractive index in that direction is different and becomes angle dependent or direction dependent. Of course, if you're propagating the XY plane, then it's fine, right? That's a circle. But if you're propagating, if it has some propagation direction along Z, then that becomes a problem. Okay? So this kind of phenomena is sometimes called birefringence. So this should say it's called birefringence. Birefringence. So essentially, you can actually show that the ordinary wave corresponds to one polarization. So one polarization, and another polarization will experience the extraordinary, will be the extraordinary wave. So essentially, if you excite this medium with a diagonal polarization, this polarization will propagate at one speed, and this will propagate at a different speed. Right? So the V pole, let's say, is the ordinary wave, and it's propagating, it has some phase shift. Now this one, the H pole, which became the extraordinary wave, was propagating at a different speed. And because it was propagating at a different speed, it gets a different phase shift. And by designing this phase shift or the width or the thickness of the medium correctly, you can have the V pole to have a 90-degree phase shift with respect to the H pole. Which means what? Which means it becomes circularly polarized. Right? So you came in with a diagonally, linearly polarized wave. So it was linearly polarized. As it propagated, it got split into two. And since they both had different phase shifts throughout the medium, at the end when they came out, they would have a 90-degree phase shift if designed correctly. And that gives you circular polarization. So this is how you make what is called a wave plate. Okay. So wave plate is essentially what I described back there. So you start with linear polarization, and then you end up with circular polarization. There's a half wave plate or quarter wave plates and so on and so forth. You can use them to do all these kind of polarization transformations. Okay. So with that, I wanted to conclude with one quick topic, since we are discussing polarization transformations, of what is called a Poincare sphere. So we discussed before in this class polarization briefly, but essentially this polarization, which is the orientation of your electric field as a function of time over one cycle, can be linear, circular, or elliptical. Right? We've seen that before. So if we revisit that, so let's say you're in real space now, and your polarization is confined to your XY plane, then in general it traces out an ellipse, and we've seen that before. It's not good. See if it gives me an ellipse. Okay, try again. Okay, I guess it doesn't want to draw an ellipse, so I'm just going to draw it freehand. Okay, so that's my ellipse. This is the major axis, and we have a minor axis. Right, so I label it as O, maybe this is A prime, and then we have B and B prime. Okay, I can make this as B prime. Okay, so this is an angle which we'll call as chi, and we have another angle which is this one, we'll call as psi. So psi is the tilt angle, and chi, yes, it was in green, it's called the ellipticity angle. So let's assume that this ellipse is essentially some size. You can describe the orientation of the polarization vector. Let's say, the vector itself is kind of rotating like this, right? So it's the electric field is tracing out, the tip of the electric field is tracing out this ellipse. right? So in general, it's an ellipse. And this orientation of the ellipse is given by the tilt angle phi, and the eccentricity of the ellipse is given by chi. So we saw that axial ratio is the ratio of the major axis to the minor axis, OA over OB, which means that chi is tan inverse of OB over OA, which is nothing but tan inverse of 1 over the axial ratio. Okay? Which means when chi is equal to 0, you get linear polarization. That makes sense because this ellipse collapses into just a line when chi is 0. And when chi is 45, then major and minor axis become equal, which means that you get circular polarization. Okay? So in general, chi is between 0 and 45. But in order to treat the right-handed and left-handed circular polarization, we can define chi to be between minus 45 and 45. And by convention, we choose plus 45 to be LHCP and minus 45 to be RHCP. So this is the IEEE convention, which is different than the optics convention. So it's important to remember that. Okay, so when chi is 45, you have LHCP. When chi is minus 45, you have RHCP. When chi is 0, you have linear. In between these values, you have elliptical polarization. Okay. Now, psi, sorry, not phi, psi is the tilt angle, which means that it lies between 0 degrees and 180 degrees, right? So essentially 0 degrees means the polarization is like this, 90 degrees polarization is V, and then 180 degrees it goes back to horizontal polarization. Okay? Okay, so now note that the angle 2 psi lies between 0 and 360 degrees, and the angle 2 chi lies between minus 90 degrees and 90 degrees, right? And these two angles, 2 psi and 2 chi, since they're between 0 to 360 and minus 90 to 90, they look like the angles that define points on a sphere, right? So if I draw a sphere, this is y, this is x, and this is z. Then I have a big sphere here now. And these points on the sphere are uniquely determined by these two angles. So if I pick a point, let's say some point on the sphere, and I have a unit vector pointing to that sphere, then I drop its projection onto the xy plane, then this angle would be my 2 psi, and this angle here is 2 chi. Right, so that goes from 90 to minus 90, so plus z to minus z, and then 2 psi goes from 0 to 360. Okay, now if I define it like this, then different polarization states correspond to different points on the sphere, because these two angles define a given polarization state, right? So on the North Pole, my psi is my chi is, say, 45 degrees, which means 2 chi is 90 degrees, and that corresponds to LHCP. Okay, and then South Pole would then be RHCP, right? And when chi is equal to 0 and phi, or psi, sorry, I keep getting confused by the names of these Greek letters, but this is psi, right? Okay, so when psi is equal to 0, you're at this point, and if you go back here, when psi is 0, polarization is along the x-axis, right? So this is horizontal polarization, and the point right behind it, when x is minus 0, when point is minus x, along minus x, you get vertical polarization, right? Because then my psi is 45 degrees. No, psi is 90 degrees, right? When psi is 90 degrees, polarization is vertical, which means 2 psi is 180 degrees, which means you're kind of pointing in the negative x direction. Okay. So this sphere, and essentially the upper half space, the upper hemisphere. So upper hemisphere is then left-hand elliptical polarization, and the lower hemisphere is right-handed elliptical polarization. Okay, and this sphere is called the Poincare sphere. It's very important because essentially diametrically opposite points on the sphere, if you pick any two points that are diametrically opposite, they would have orthogonal polarizations. So horizontal and vertical are orthogonal, LHCP, RHCP are orthogonal, and then this point along y-axis would be kind of a diagonal polarization that way. Y-axis back there would be diagonal polarization this way, but still linear. Right? So any point on the equator is linear polarization. These 2 points are circular polarization, and any other point is elliptically polarized. Diametrically opposite points are orthogonal. So when you're designing a system, if you have a wave that is polarized here, and you have a receiver polarized on the opposite point, then you will receive no power, right? Because those two waves would not be matched, polarization matched. Okay? Okay. So even when you're designing these half-wave plates and so on, essentially it will give you a transformation on the Poincare sphere from here to here, here to there, or there to there, here to here, and so on. So knowing how you're moving on the sphere can help you visualize what a given wave plate is doing or what a given polarizer is doing. Okay? All right, so since we're on this topic of polarization, maybe we can talk about one last interesting topic, which is the polarization of the sky. Okay, so essentially we want to know if the blue sky that you see when you look up into the sky, is it polarized or not, right? And the answer to that is that it is actually polarized. Although the sunlight, which is leaving the sun, is not polarized, unpolarized basically means it has all polarization states, right? So light leaving the sky has points all over the Poincare sphere. Every single polarization state exists just because it's such a random process, right? But scattering from the sky, which gives it the blue light, is not completely random, and it can actually be polarized. It is, in fact, actually polarized. So scattering from the sky is called Rayleigh scattering, which we haven't seen yet. Maybe we'll see it later in this class. So Rayleigh scattering occurs when the wavelength is much larger than the size of the particles. Okay, so in the air, it's like N2 molecules and O2 molecules, and wavelength is usually much larger than those guys. Okay, and this Rayleigh scattering is also the reason why the sky is blue, which we won't discuss now. But essentially, when you have Rayleigh scattering, you can treat each scattering particle as a dipole. And because the wavelength is so large, each of the scattering particles behaves like some kind of a small dipole, like a small current source that's oscillating back and forth. So you have an incident field that comes in, and then every molecule basically just oscillates back and forth a little bit, and it radiates like a small dipole. So under the small dipole approximation, we can actually see why the sky is kind of polarized. So we'll take two cases. So first case is, let's say this is the Earth, and then you're standing on the Earth, that, and then the sun is kind of on the horizon, somewhere there. So that's the sun. So I'm just going to draw it like that. Okay. So we know that sunlight, as it propagates over a long distance, if you look at this kind of plane wave picture, all of these rays that are coming out of the sun correspond to plane waves, different plane waves, right? So since they're propagated to such a long distance, the plane waves that are actually coming to the surface of the Earth, all these rays are basically parallel. So you can treat all of this as just a single plane wave. Single plane wave that's propagating like that. Okay, and this is your wavelength, whatever, right? Wavelength and so on and so forth. Okay, so since it's just a plane wave, it can have polarization states that are either like this, right? Or it can have polarization. So let's put an axis. So let's say this is the x-axis and this is the y-axis. Okay, so polarization can either be y-directed or it can be z-directed, like that, or some combination of y and z, right? So it can be even circularly polarized in this yz plane. Okay, so once this hits a particle, once it hits a particle, this particle can oscillate in this axis, or it can oscillate in the z-axis, right? Which means radiation from this, in both cases, it's a dipole, so it radiates either like this, or it radiates all over. So if the dipole is like this, then it radiates the electric field, so the radiation pattern is equal in all directions. If the dipole is like this, then the radiation pattern is like this. So in both cases, you see it. So light coming in this direction is unpolarized. Right? So this case would be unpolarized. Okay, but there is also some light that goes out here and then scatters. I mean, since it's coming parallelly, let's say, there is some light that scatters from here and reaches your eye. What happens to that? Right, so once again, we have this same scenario. Out here. So maybe I'll erase this one now, and then move this out here. Okay, now what happens? Now when these dipoles are scattering, right, you have a dipole that's scattering like that, and you have a dipole that's scattering like this. Now this dipole doesn't radiate towards you. There's a null in your direction. Only this one scatters towards you, right? Because this one scatters in all directions or radiates in all directions. So which means that the light coming from above you would be Z-polarized. So even if there's some circular polarization component, you don't see part of it. You only see the component that's Z-polarized. Okay? Now, of course, there is also scattering from the wave that went there and then scattered back to you in this direction, and that also will be unpolarized. But now there is a wave that went behind you, sort of back there, and then it scattered towards you, right? So if you look from above, if you are here and the sunlight is coming from there, and it's the scattering that came like that. So in positive Z and negative Z, what happens to that? Now in positive Z and negative Z, you end up with the same case. So you have this one and this one. Now this one reaches your eyes because you see this dipole, but you don't see this. You're in the null of this dipole, right? So that light would be Y polarized. Right, so essentially when you look, if you take a polarizer and you look at the sky around you, looking towards the sun and away from the sun, you will see unpolarized, right? Looking back, looking in orthogonal along the surface of the Earth in that direction along plus z or minus z, you will see bipolarized light. And when you look straight up, you will see z polarized light. Okay. So the sky, in fact, so if you use a polarizer, you'll see parts of the sky are dark, parts are brighter. If you look up, it will be bright and dark, depending on how you orient the polarizer. Okay, the other case is when, so I'll go through this one a little bit more quickly. We'll have the same situation. Person standing up here. And now the sunlight is kind of coming from above. So the sun is right there. Okay, so polarization can be either like this or it can be like this. Like you can't have polarization along y because that wouldn't be a plane wave, right? Okay, so now in this scenario, what happens? When you look up, again, you don't see any polarization. So if you look up, it would be unpolarized. But if you look to the right, you will see only this component, right? As in if you look out here, you'll see this component, which would be polarized. If you look out here, you'll see this component polarized. If you look in positive z and negative z, then you will see this component. Right? So once again, now, light coming from above is unpolarized. But if you look along the horizon, the polarization will start to rotate between V and H. Not V and H, sorry, it's just H, but it's always sort of in along phi hat. So as you're going around, so let's say this is from the top view, you're standing here. When you look around, polarization will be like this, right, tangential to this circle, which is the phi hat direction. But if you look above, then there won't be polarization. So it would be unpolarized. Okay, so depending on where the sun is, the polarization of the sky changes, the scattered field from the sky. And that's actually what bees use to navigate. Bees use this polarization map, let's call it, map to navigate. So if you know which side, if you know where the sun is, or even if you don't know where the sun is, by knowing what the polarization status of the sky, you can orient yourself with respect to directions. Okay. One more interesting topic on polarization. It's called Heidinger's brush. So, did you know that your own eyes can also see polarization with the naked eye? You don't need a polarizer. And that's called a Heidinger's brush. So it looks something like this. It looks like kind of a dumbbell shape. So there's a bit of yellow. And then there is also some blue. It's very faint. I'm drawing it kind of bright here, but something like that. Maybe I shouldn't draw that part. Something like that. Okay, so essentially, if you have a polarized light source, let's say an LCD screen, and I've tried this myself, and many people actually, I don't know if everyone can do it. I don't think everyone can do it, but some people have a gene which allows them to identify the polarization state of the light coming out. And you can try that for yourself if you want. You can look up what Heidinger's brush is, and there are some, I guess, tutorials on how to actually see the polarization. So some people are really sensitive to this, and they can even see the polarization of the sky. And apparently, there are some evidence that people used to navigate, or I guess Vikings used to navigate thousands of years ago, using the polarization of the sky. Some of them, maybe they use this Heidinger's brush phenomena, or they would use a quartz crystal and the birefringence phenomena to kind of detect what the polarization of the sky is. And from the polarization of the sky, even when the sun is set, you can tell where the sun set or which direction is north, south, and so on, right? So that's also something interesting, and I recommend, I suggest if you're interested, you can try and pick up an LCD screen if you have one, or a polarization, or buy a polarization filter and then put it in front of your screen and try and see if you can see the Schrodinger's brush. I've been able to see it in the past when I've tried. That's another interesting polarization phenomena. Okay, so I'll stop here for today. So we discussed many different topics. We started from plane waves in lossy media. We discussed the complex K vector, and we went to evanescent waves from that. We saw that, they have some kind of power that flows along the surface, but not away from it when they are formed at the interface between a surface and between dielectric and another dielectric. We haven't really seen how that's done. We'll see that when we do waveguides. But we saw that kind of from a high level. We saw how to excite evanescent waves. We saw the Scratchman configuration, and surface plasmon resonance as an example. Then we did plane waves in anisotropic media. We considered the case of uniaxial medium and birefringence phenomena and how wave plates are made. And lastly, we discussed the Poincare sphere and polarization states. And we looked at some cool examples of polarization in the real world. Okay, hopefully that was an interesting lecture. In the next lecture, we'll look at plane wave reflection and transmission through media, and we'll take it from there. Also very interesting phenomena in that example. Okay, if you have any questions, you can leave them in the comments below. If not, I'll see you in the next one. Thank you.